Okay, good morning, everyone. We're going to continue talking about communication systems and specifically digital communication systems. We just finished talking about digital modulation, and now we're going to move on to source coding. All right, so here are the source coding notes, and what we see on page 1 of the source coding notes is the block diagram, a high-level block diagram of a basic digital communication system. So let's quickly review that. So in this diagram, we see we have an information source that gets fed into what's called the source coding block. And if you remember the source coding block, we're going to put the analog to digital converter, the digitization, the sampling and quantization functions that are part of digitization inside the source coding block. Then the source coding block does a second function. It performs a second function called data compression. After that, we have bits. We have compressed bits get sent to a channel coding block. The channel coding block is going to introduce redundancy to give us robustness to noise in the channel. Then we have the modulation block, which takes these bits and embeds them into a transmit waveform. Okay, and this digital modulation block is the one we just finished, right? Then this transmit waveform, which has our information symbols encoded in it, gets sent through a channel. Okay, channel is just a conditional PDF. X is the input, Y is the output. It's a stochastic object, so it's characterized by a probability distribution, probability of Y given X, and this distribution is comes about because there's random noise that's added into the channel here. And often we model this as additive white Gaussian noise channel. Here I write it more generally because it can be more than just additive white Gaussian noise. It can be multiplicative noise. There can be a whole bunch of different things, intersymbol interference, and so on. Well, anyway, the channel output Y is received and demodulated. Okay, and again, that's the topic we just finished. The demodulation is going to generate bits. Right? We took in the modulation, we have bits embedded into the transmit waveform. Here from the transmit waveform, we recover the bits. Then we do the channel decoding, which is the reverse of the channel encoding, and then the source decoding, which is like the decompression, the reverse of the source coding. And so the next two topics are going to be source coding and channel coding. So we're going to do source coding first. Okay, the function of source coding is to convert a sequence of source symbols into a sequence of bits, right? I'm not going to talk about the sampling and quantization. We already discussed that when we discussed PCM. All right, so right now in the topic of source coding, we're going to focus on the data compression part. So I want to convert a sequence of source symbols into a sequence of bits, and we want to use as few bits as possible. So that's why we call it data compression. We want our data representation of the source to consume as few bits as possible, right? Now this compression can be lossless, meaning we don't lose any information, and it can be lossy, we can lose information. In our discussion about source coding, we'll only focus on lossless data compression. But let me give you an example of lossless and lossy compression. So for example, if you have an image that you represent as a PNG file, right? That's a lossless compression algorithm. If you represent an image as a JPEG file, that's a lossy compression algorithm. How do you know that JPEG is lossy? Well, when you convert something to JPEG, it will ask you for a quality parameter, right? It will say, do you want this thing to be low quality, medium quality, high quality? Well, that should give you a hint. If you can generate different qualities, then this is lossy compression because I can control the quality. I can throw away less information, medium amount of information, or more information, right? The more information you throw away, the smaller the file is, right? So the lower the quality of JPEG, the smaller it is. So JPEG is a lossy compression algorithm. PNG is a lossless compression algorithm, okay? Now, data compression is not only relevant in like when you're transmitting information from point A to point B, it's also relevant when you store information. For example, on your hard disk or on a CD, data compression is used. So I'm sure many of you know this idea of zipping files, right? Either using WinZip or PKZip, right? These algorithms are doing exactly this. They're doing source coding or data compression. All right, so this is an important topic, right? Because we want to, when we want to transmit data, we want to send as few bits as possible, because transmission is expensive. It's expensive maybe from a dollar point of view. It's expensive from a power and resource point of view. So that's why data compression and source coding are important. Okay. So the first, so our problem is that, so the problem we're going to address is that we're going to assume we start off with a set of symbols that we want to transmit. So the sampling and quantization has been done already, and we end up with a sequence of symbols. That's if you have a continuous time signal, an analog signal. But we could also, our data that we want to send could naturally be discrete. For example, if you want to send a file consists of letters A, B, C, D, E, F, right? So that's my first example. Okay, you have English language that consists of these alphabet characters, A through, in the actual English language, we have A through Z, 0 through 9, and the punctuation, right? For my example here, I'm going to just say, suppose I have a 6-letter alphabet, A through F. The first thing I'm going to do is I'm going to look at what's called a fixed length code. So a fixed length code maps these alphabet characters, or more generally, we'll call them symbols. Okay, so we're going to map these symbols to bits. And a fixed length code, of course, maps it to a fixed length, a code word with a fixed number of bits. So we know that, for example, ASCII is an example of such a mapping. Okay, the ASCII represents characters as 8 bits or 1 byte, right? Now, if we have 6 symbols here, A, B, C, D, E, F, how many bits do we need to represent them, and why? You need to differentiate at least 6 things, and with bits we got powers of 2, so we'll need at least 3 bits, because if we use 2 bits, we can only differentiate 4 items, and 4 is less than 6. So yeah, we need 3 bits, right? So here, code C0 consists of 6 3-bit code words, right? And I'm showing the mapping from symbols to code words. So A through F are symbols, the 0000001 are code words, and the set of code words and the mapping is called a code. Okay, so C0 is my code, or my source code. Let's hopefully it's not confusing. At this point, it shouldn't be confusing. Yes, I know code has to do with programming, but in here the word is reused to mean a mapping. In source coding, it's a mapping between symbols and code words. In channel coding, it's going to be a mapping between messages and code words. So when we use source coding and channel coding in the same idea, I'll say source and channel code. Otherwise, sometimes I just may use code. So here, this C0 is a source code, okay? And a fixed length code is when the length of the code word is fixed, right? And again, we can define a few properties of this source code. We're going to define the average code word length. Now, in this case, the code word length is fixed to 3. So the average over all the symbols is, of course, 3, right? Now, the reason we want to average is we will often model, excuse me, we'll model our source as a random quantity with a certain probability mass function. For example, let's take the English language. Can you tell me what is the most used letter in the English alphabet? Does anybody have a guess? We can see that the probability of, you know, E occurring or A occurring is much more, for example, than the probability of Z or Q, right? So our source is actually a random variable. It's a random quantity, right? When you look at what is the next letter coming out of the source, the next letter I'm going to encounter, it's more likely to be E than Z, right? That's why we have a probability mass function over the letters, and we can talk about average code word length. But of course, in the fixed length code, the average code word length is fixed, so the average is fixed, okay? We can bound the average code word length. We know that if you have M symbols, for example, in this case, we have 6 symbols, so we know we needed 3 bits, right? like for example, if you take log base 2 of 6, that's not an integer. So you need to go up to the next power of 2. So that's all this bound is saying, that the average code word length L bar is lower bounded by log 2 base m and upper bounded by log 2 m plus 1, right? And this makes sense. In this case, log 2 6 is not an integer, but it's still a lower bound. But upper bound is log 2 m plus 1, which is going to be a little bit above 3, right? We can actually do better by putting putting ceilings on these things, right? I could have put a ceiling on this and it would have also worked. Okay, but these bounds are still accurate. So this average code word length is important because it's going to be our performance metric for how efficient the code is. The lower the average code word length, the more efficient the code is. Okay, because remember, we have control over this mapping. So, and since we want to reduce the number of bits set, we want our average code word length to be small. In fact, that's how we get data compression. Okay, all right. So this was fixed length code. It's a very simple idea. The counter to that is something called variable length codes. Now, the length of a code word in a variable length code is not fixed. That's why it's called variable length. And the idea, and we discussed this idea when we first started our class. Remember, I went through the entire set of topics and we talked about the idea of variable length codes. And the idea there is to assign shorter code words to more frequent symbols. So for example, in my example here, I show you the letters A through F again, but I give you the frequency of occurrence, or how many of those particular symbols occur in a set of text that I want to transmit. So if I have 100 letters, here I'm telling you there's 45 A's, 13 B's, 12 C's, 16 D's, 9 E's, and 5 F's. Okay? And here is a possible source code. C1 is a possible source code. Since A is very likely, I'm going to assign A to be a single bit, 0. And then B, C, D, E, and F are assigned as follows, right? D is the second most likely symbol. Is there a reason why I can't assign 1 to D? Like I assign 0 to A, why can't I assign 1 to D? If D was 1, then for example, 100 could be DAA, or it could be C. So that's why, so the design of a source code is going to take that into account, okay? But anyway, in this case, this is a C1 is a variable length source code. And let's look at, if I represented this file in ASCII, 8 bits per symbol, I would need 800 bits. And with 3 bits per symbol, I would need 300 bits, because there's 100 symbols here. With C1, I only need 224 bits. And this is all lossless source codes. What we just discovered was that unique decodability is important. That given a bit stream of a variable length source code, it needs to be uniquely decodable. If you have multiple things it can decode to, all bets are off. You don't know which one was sent. Now, can I ask you a question? Is a fixed length code always uniquely decodable? So the question is, if I use a fixed length source code, the one on the previous page, this one, is it uniquely decodable? Yeah, it's always uniquely decodable because all the code words are different, right? But with a variable length source code, all the code words being different does not mean it's uniquely decodable. Okay, so on this slide, we saw our first sort of view, at least when talking about this set of nodes, our first view of data compression, right? We went from 800 bits to 300 bits. In fact, going from 800 to 300 is not really compression, because ASCII is overkill for this. I mean, you would use ASCII when you are when you want to use a protocol, like a fixed standard. ASCII is a standard. My 3-bit code is not a symbol. Sorry, it's not a standard. But if I have a proprietary system, I don't need to use a standard. So let's compare to the 3 bits per symbol, which was 300 bits, okay? And the variable length code can get to 224 bits. So that's pretty good, right? That's 76 less bits that I have to store and compress. And remember, this is for free, right? You paid, the only price you paid was a little bit of computation. Okay, no other price you paid, like bandwidth or anything. Okay, in fact, it helps you save bandwidth. All right, so what we're gonna do is we're gonna study the theory of variable and source codes, okay? So in doing that, we're going to first talk about some properties of source codes: singularity, singular, non-singular. And this is pretty straightforward. Each code word is mapped to by at most one symbol. If two symbols can generate the same code word, we have a problem, right? It's not uniquely decodable. Or we are going to require that our code is non-singular, okay? The second thing we're going to require is that our code is uniquely decodable, that a sequence of received bits maps to only one sequence of symbols, right? And we were able to construct codes that are not uniquely decodable on the previous page, right? So these are two important characteristics of all valid source codes. If you don't satisfy these two, it's not a valid source code because you can't use it, okay? Now, the third property is going to be a good property to have. It's not required to function as a source code. To function as a source code, all you need is actually unique decodability. Actually, if something is uniquely decodable, it's also non-singular. So we actually just need to have unique decodability, okay? Prefix-free is a property which helps in decoding, okay? In a prefix-free code, no code word is a prefix of any other code word, okay? So we'll see later why that comes out to be a useful property. I mean, in short, what it does is once you find a code word, you can decode to it, okay? Because you know that once you find a code word, it cannot be any other code word because no code word is a prefix of any other code word, okay? So let's take a look at this example here with A, B, C, D, E, and I designed it. The variable length code is 0, 1, 1, 1, 0, 0, 1, 0, 0. This is not uniquely decodable. First of all, we see it's not prefix free. It's not prefix free because 0 is a prefix of this code word, right? So if you look at 0 and you look at 0, 1, well, 0 is the start of this. So you actually don't know if when you encounter 0, you don't know if it's A or if it's the beginning of D. That just means it's not prefix free. That's okay. Not prefix free is not really a problem. But not uniquely decodable is a problem. For example, if I send AA, are you going to decode as AA or E? Right? You can, and that's what I point out here. So it's not uniquely decodable. So there's a bad code, but I wanted to give you an example of this. Before we continue with some more examples, this is how the three properties fit in. Non-singular is the largest set of code words, the largest set of codes. But remember, non-singular is not good enough. We need uniquely decodable. And uniquely decodable is a subset of non-singular. That's why I told you uniquely decodable implies non-singular. Then a subset of uniquely decodable codes are prefix-free. So prefix-free implies uniquely decodable. So we are going, in fact, at the end of the day, we are going to design prefix-free codes because they are useful for decoding efficiently. Okay, uniquely decodable is all we need. Okay, but prefix-free is very useful. So this is an example of a not uniquely decodable, not prefix-free code. Here's an example of a non-singular code, just so we can see it, right? A gets mapped to 0, B gets mapped to 0. This is obviously singular, right? Because two symbols got mapped to the same code word. Here's a non-singular code, right? A code is non-singular if every code word is different, okay? Then we have the idea of uniquely decodable. The transmitted sequence can be uniquely decoded from the encoded bit sequence. So here's a 3-symbol code. So this is 0, 0, 1, 0, 1, 1. Now, do you see that this is not prefix free? Because 0 is a prefix of 0, 1, and 0, 1, 1. In fact, 0, 1 is a prefix of 0, 1, 1. Okay, so this code is not prefix free, but this code is uniquely decodable. If I receive a 0, then what do I have to do? We have to look at the next bits. If the next bit is a 0, then I know that the first bit, I can decode the first bit to A. Now, if I get a 0, 1, I have to wait for the third bit. If the third bit is a 0, then the 0, 1 was a B. If the third bit is a 1, then it's a C. So you see there's a decoding delay. Even though you find a code word, you cannot decode. You have to wait until there's no uncertainty left. So this 0 and 0, this code M3 is uniquely decodable, but because it's not prefix free, I can't decode as soon as I find a code word. What you'll find with the prefix free code is that as soon as you find a code word, you can end. The code M2 here, this code M2, which is shown here, is not uniquely decodable. Even though it looks like a nice code, it's not uniquely decodable, and here's the example. Okay, so I think we understand properties of codes. The takeaway message is we need uniquely decodable codes. We want prefix-free codes, okay? Because prefix-free is going to allow us to decode efficiently. Prefix-free means no code word is a prefix of another code word. So M3 that I showed here is not prefix-free. C1 here, this code is prefix-free, okay? The practical advantage of prefix-free codes are that whenever you find a code word, you can immediately decode to the code word. That means you don't need to wait, no look ahead, right? What you guys were describing, meaning waiting for other bits, is sometimes called look ahead. Now, the claim is that prefix-free implies uniquely decodable. Prove that if a code is prefix-free, then it is uniquely decodable. So this is an exercise for you guys, okay? That's why I put that here. Prefix-free code, if you think about it deeply, can be represented as a tree, okay? And in fact, if it's a binary code, it's a binary tree. So for example, here's a code, here's code C1, and here is its representation as a binary tree. So we see that A is 0, but all these other code words start with 1. That means there's a split from the root, 0 and 1. 0, it will be a leaf node because no other code words start with 0, and actually that's symbol A. But every other code words, B, C, D, and F, will come from the second branch because they all start with 1, right? So we see immediately that there's a split at the root, a 0-1 split, and you can kind of do the same thing now. You see that the second bit is either a 0 or 1. So for B, C, it's 0, and for D, E, F, the second bit is 1. That means there's a split here. And when you split the 0 here, you will get B and C. And down here at the leaf nodes, you'll get D, E, and F. So I've given you the idea. I think you can now figure out that every prefix-free code is a binary tree. And in fact, there's a one-to-one map. Every prefix-free code is a binary tree, and every binary tree is a prefix-free code. There's a very useful result called the Kraft inequality. Okay, it's named after somebody called Kraft. In fact, the general version of this is something called the Macmillan-Kraft inequality, because what Macmillan did was he generalized it. Okay, but what Kraft proved is that a binary prefix-free code with the following code word lengths, meaning here, okay, with code word lengths L1 through LK, okay, so that means a binary prefix-free code with these code word lengths exists if and only if, very strong condition, if and only if this is true. If and only if the sum of 2 to the minus Li is less than or equal to 1, right? And in fact, the proof of this is because a prefix-free code is a binary tree. Okay, if you look at this binary tree and you do that operation, you will see that if it's a binary tree, this has to be the case. Okay, so remember the length of the code is the depth of the binary tree. The if and only if means that this is a sufficient and necessary condition for the existence of a prefix-free code. What this means is two things. It means that if the Kraft inequality holds, then there exists a prefix-free code. This one says, the reverse says, every prefix-free code satisfies the Kraft inequality. So we cannot use this result to find a prefix-free code, but we can use the Kraft inequality to see if a prefix-free code exists with a given set of code word lengths. Let's look at this code here. What are the code word lengths here? 0, 2, 2, 2, 2, right? Can you apply the Kraft inequality here? So we're going to do, this code word length is 1. So we're going to do 1 over 2 to the 1, which is 1/2. This one is code word length is 2. So it's 1 over 2 squared, which is 1/4. So we have a 1/2 here, 1/4, 1/4, 1/4, 1/4. When you add that up, you get 1.5, which is more than 1. So that means there does not exist a prefix-free code with length 1, 2, 2, 2, 2. That means no matter how hard you try, you cannot find a prefix-free code with length 1, 2, 2, 2, 2. Now let's take a look at M3. What are the code words lengths for M3? Yeah, 1, 2, 3. Can you apply the Kraft inequality? So let's do it. It's 1 over 2 to the 1, which is 1/2. This is 1 over 2 squared, which is 1/4. And this is 1 over 2 cubed, which is 1/8. So this is 1/2 plus 1/4 plus 1/8, 7/8, right? And that's less than 1. Hey, wait, there's a problem. So M3, I told you, is not prefix-free because it looks like this satisfies the Kraft inequality. So why is this not prefix-free? But we know this is not prefix-free. So what's wrong? KI tells us if a prefix-free code exists, not if the code is prefix-free. Okay? The Kraft inequality does not help you check if a code is prefix-free. The Kraft inequality helps you check if one exists. And we know one exists because I told you, right? When we were on this slide, I constructed a prefix-free code with these lengths. This code is prefix-free and it has the same code word length. So the Kraft inequality is not violated. So Kraft inequality was a sufficient and necessary condition for the existence of a prefix-free code. Okay? And so, you know, for example, for 1, 2, 2, yes, it does exist. So what you can say is if the Kraft inequality does not hold, no prefix-free code exists. Okay. Now the beauty of the Kraft inequality is it's also a sufficient and necessary condition for the existence of a uniquely decodable code. Remember, this is completely different statement and very powerful statement. This actually is Macmillan's contribution. That's why Kraft inequality is sometimes called the Macmillan-Kraft inequality. Because what Macmillan showed is that this beautiful condition here doesn't only tell you if prefix-free codes exist, it's actually sufficient and necessary for uniquely decodable codes, which remember was our main requirement. Remember, we require uniquely decodable codes just for basic functionality. We desire prefix-free codes because they help us decode faster, right? The decoding latency is reduced. What we're going to do when we return is we're going to talk about a specific type of prefix-free code called a Huffman code. So a Huffman code is a variable length code. It's a prefix-free code, and it's an optimal code. It's optimal in the sense that it has the minimum average code word length.